Behind the ordinary objects that surround us in our everyday lives lies something extraordinary. Incredible stories of ingenious solutions to problems most of us never knew existed. So what mysteries are concealed in everyday things we take for granted? Icebreakers, money, bowling alleys. Behind the ordinary is the extraordinary. Now revealed as we go behind the scenes, inside the machines, to find out, how do they do it? It's the middle of winter in eastern Canada. It doesn't look it, but this mesmerizing frozen landscape is a river. The mighty St. Lawrence, one of the most vital trade routes in North America. But if the river's frozen, there's no trade. So how do you keep the shipping lanes open on the St. Lawrence River in near Arctic conditions? How do they do it? There's a very special ship on the St. Lawrence which is prepared to sail where no other ship dares. This is the Amundsen. This dauntless vessel has the task of forging a path through ice sheets which are as much as 2 meters thick. Ice like this would sink a weaker ship, but the Amundsen is an icebreaker, specially designed to smash through the St. Lawrence's frozen surface. What the Amundsen does is immensely important. The St. Lawrence River is over 1,600 kilometers long. A quarter of the entire population of North America depend on it, as they're linked to the sea. In order to keep it flowing, the river is constantly charted for dangerous ice conditions. As the Amundsen surveys the St. Lawrence from sea level, a reconnaissance helicopter gathers information on the icy waters from above. The helicopter communicates its findings to a control room in Quebec City. This is the Canadian Coast Guard Control Centre, a maritime version of air traffic control. The Coast Guards monitor every vessel within their jurisdiction along almost 6,500 kilometers of coastline. It's the job of ice specialists like Jean-Yves Roy to interpret the data and spot potentially hazardous situations.
Okay, right now on the screen here, we have an ice chart that is produced by the helicopter, and they draw the ice conditions. Plus we have here, we have our cameras here that look at different places. As you can see here, the ice is moving everywhere, so we don't want the ice to stop anywhere.
As long as the Coast Guard can see that the ice is flowing steadily, then marine traffic should be able to pass safely through the freezing waters. But when the temperature drops severely, dense ice packs can form in a matter of hours, coming together to block the St. Lawrence. It's time to call the icebreaker. The icebreaker's hull is far stronger than that of an ordinary ship. In parts, the steel plates are a massive 60 centimeters thick. Its reinforced bow heads straight for the ice, smashing it as it moves forward, plowing slowly through the frozen river. But the Amundsen relies on more than an incredibly thick hull. It also needs an unusually powerful forward thrust. Below deck are 6 huge engines, each as powerful as a freight train. Between them, they generate a massive 18,000 horsepower. That power is transmitted to the Amundsen's two propellers via these giant rotating shafts. But even for the Amundsen, sailing straight into blocks of ice is perilous. It is vital that the crew finds the best route through. So how do they do it? While all ice may appear the same to you and me, a trained eye can recognize important differences.
As far as the ice is concerned, the first part of our trip will get us to light ice, very kind of thin, and then we're going to have some gray ice, which is a little thicker.
Experience and a trained eye is often not enough. When the going gets tough, the only answer is to stop the icebreaker and for the ice specialist to go overboard. His job is to gather data on the thickness of the ice, and the only way he can do it is by digging around. By boring a hole into the ice and measuring its depth, the Amundsen can avoid the more solid areas and carve out an easier path elsewhere. The data collected in the field is sent back to the Coast Guard Control Center, where all the Amundsen's movements are monitored. Today, the Amundsen has the job of ploughing a path through the frozen river to enable the 39,000-ton Croatian bulk carrier, the city of Dubrovnik, to enter port in Quebec. The ice which the Amundsen breaks reforms with incredible speed in this freezing cold water, so for safety's sake, the trailing ship must remain close to the Amundsen. But this brings its own danger.
If we have a major mechanical problem, we have very, very few seconds to react, and it's the same thing for the other ships. So there's always the fear that something goes bad and then we get rammed over by the other vessels. So that's something it's something we don't like to think about, but it's kind of a nightmare.
The city of Dubrovnik, on the last leg of its journey from sunny Brazil, silently trails the Amundsen through the ice. Captain Alain endeavors to keep the bulk carrier as close as possible without endangering his own, much smaller ship.
What I'm doing is adjusting the ship speed to maintain the same distance between our ship and the ship we're escorting. This is the target you see right here on the screen. So I'm trying to keep the same distance. Actually, I'm going to let it just come in a little closer to here, then maintain that distance all the time.
Within hours, the snow starts to fall thick and fast, reducing visibility still further. Both vessels need to pay close attention to each other's every movement. They're nearly home. As the ships arrive in Port Alfred, the Amundsen's final task is to break the surface in the icy port for the Croatian vessel to dock. The Amundsen's job for today is done. The city of Dubrovnik has made it through the treacherous ice to safety. Behind the ordinary is the extraordinary. Coming up, banknotes can rip, tear, and wear out. But this bubble is making indestructible ones. The secrets behind making money, next on How Do They Do It? Money. Across the world, 100 billion banknotes are produced every year and spent many times over. The total value of notes in circulation is more than $1 trillion. That's 1,000 million dollars. But the trouble with all this money is, it doesn't last long. The life expectancy of a banknote is just over a year. And worse than that, many banknotes are still relatively easy to forge. So how do you create an almost indestructible banknote which is all but impossible to forge? How do they do it? Welcome to Melbourne, Australia, where dirty money is a thing of the past. Faced with the twin challenges of banknotes rapidly wearing out and increasingly sophisticated methods of forgery, the Reserve Bank of Australia decided on a radical break with tradition. In 1988, they started to experiment with a bold new kind of banknote. One that was virtually indestructible. A banknote which was made of plastic. And it's such a success, it's catching on all over the world, from New Zealand to Nepal. To make their plastic money, the Australians start with these small granules of polymer. The tiny beads are melted at the top of this huge metal tube. And what you can see here is the molten polymer cascading down. As the 250-degree liquid travels, it is cooled by small jets of water. Now it's ready for the next stage in the process. And if you've ever blown bubbles, prepare to be amazed. This is one of the biggest bubbles on Earth, 5 stories high. It's so big, in fact, it's impossible to see it all at once. This is just the top. As long as it's maintained at the correct pressure, the walls of the bubble are always the same thickness. But it needs constant monitoring. In total, this huge bubble will be stretched 20 meters. Towards the bottom of the bubble, the polymer is gathered up in rolls, and it starts to resemble cling film. An infrared gauge checks that the film has the correct thickness. The polymer sheets are wrapped into rolls. Each roll contains over 8 kilometers of film and weighs 1.5 tons. Now they've created the polymer film, there's another problem. How do you print onto clear plastic so the ink doesn't rub off? The solution requires a massive press and some seriously gloopy paint. The film is painted white up to 5 times on each side, creating an opaque, adhesive surface that's ready to receive the banknote design. It may look like they've missed a bit, but in fact every note will have a small transparent window. A strobe light is used to check that the windows are all there. This is one of the most important characteristics of the plastic banknote, because this is where one of the key security features will go. The rolls of notes are sent up one level, and it's here that a counterfeit-proof image is burned into the window. A technician carefully monitors the process as a laser etches 5 tiny images into each window in 20 billionths of a second.
This pattern is a diffractive optic, which is very similar to a hologram, except then that you can project this with a laser pointer, or you can look through it at a point source light. Very, very sort of high-tech security feature. It's very, very difficult to counterfeit. In fact, we're not aware of anybody having done it as yet.
Now the polymer can be cut into sheets. They're almost ready for the next stage, the printing of the banknote design. First, the background colors are added by this special machine, which prints on both sides of the note simultaneously. Then the notes need to be transferred to a second machine for their next layer of ink. The worker fans out the sheets to ensure they don't stick together. In his hands, he's holding what will become almost $750,000. The next printing press adds another layer of ink, the bolder colors and fine details. By varying the thickness of the ink, it gives the surface of the note a ridged texture that should make it easy to distinguish the real thing from a forgery. The notes are almost finished, but they still lack one key security feature: their unique serial numbers. The counter is set by hand to the first number of the next sequence, and the machine is ready to start numbering the notes. It can number 2.5 million notes in one 8-hour shift. A few kilometers away on the local beach, there's bound to be one absent-minded swimmer who's left his money in his pocket. But in Australia, it doesn't matter. For this beach bum, his dripping loot will be just as acceptable to the local bartender as before he went into the water. Behind the ordinary is the extraordinary. Coming up, the secrets behind bowling. Next, on How Do They Do It? Ten-pin bowling. Apparently, it's the world's second most popular sport, after football. More than 100 million of us do it every year. In the US, it's a $10 billion industry. And to keep that industry going, we need to be able to play at least 10 games an hour, and that means resetting the pins in just 8.5 seconds. So what does it take to keep the world bowling? How do they do it? Bowling hasn't always been played at such breakneck speed. The Sheephead pub in Edinburgh built its 10-pin bowling alley in 1871, and the game has been played the same way here ever since. This version is much closer to the centuries-old match of skittles. The balls don't have holes for your fingers, but otherwise the equipment looks pretty much the same as 10-pin bowling today. But the pace is very different because there's a person, not a machine, respotting the pins at the other end. But hey, these guys are in no hurry.
You end up with a very strong right arm from lifting the beer and lifting the ball, yes.
So how do you create an alley which can reset its own pins in a matter of seconds? To find out, we've come to the AMF Kubica factory in Virginia, USA, where they make the machines known as pin spotters. They've been making them since 1945, and demand is huge from all around the world. 11 are made by hand here every day from 4,000 individual component parts. The pin spotter's job is to ensure that the knocked over pins are removed and a new set of pins is ready for the next throw in 8.5 seconds. These pin spotters live in a parallel universe, hidden from public view at the back of the alleys. But how do they work? Every pin that's knocked down is swept off to a carousel at the back and positioned the right way up. Next, they're fed onto a plastic tray, but they need to be distributed into their proper positions. These pins are then respotted. Only one of the 10 pins can fit into one of the holes. But how does the arm know where to put each pin? The answer is with the irregular shaped rail on this white plastic wheel. There are 10 notches on the wheel which direct the pin distribution arm. As the wheel revolves, the mechanism repositions the arm so that each of the 10 pins ends up in its correct space. The engineers know that the spotter should be able to reset at least 6,000 pins before it needs any maintenance. But when it does jam, it needs a human called a pin chaser to sort it out. The machines are generally so reliable, though, that he can look after 24 lanes at the same time. So now you know what happens with the pins. What about the ball? It too disappears into an unseen world where it finds its way to a hole down the side and is then propelled under the lane back to the bowling area. A bowling ball can weigh up to 16 pounds and is usually made of plastic. These sample balls are stringently tested in the factory. A ball will typically play a punishing 50 games a day and should last at least 5 years. The test ball will pass through this loop-the-loop machine 4 million times.
This machine runs 24/7. It's non-stop. The only thing that really stops this machine here is a power failure.
This is literally a job for a ball breaker.
My job is to break things. And that's basically what I do. I put it to the test and see what does it take to break it and what does it take to make this part fail.
So next time you're out at the bowling alley, spare a thought for the pin spotter and the pin chasers working feverishly behind the scenes. Behind the ordinary things that surround us in our daily lives are miraculous advances in engineering, which we rarely get to see. Ingenious solutions to problems most of us never knew existed. Since this program began, the Amundsen has smashed through another 72,000 tons of ice. $750,000 worth of plastic banknotes have been produced, and 100 pins have been repositioned perfectly in one bowling lane. Even the most ordinary objects have an extraordinary story to tell. We only have to watch and listen.